This is what is a fermion part 2. And I will first try to give a very short summary of what we talked about last time. What we talked about last time was that if you have a system of n fermionic modes, this corresponds to having in your Hilbert space or in a space of operators a representation of this algebra, which I called the Clifford 2n-dimensional algebra, which we said is the algebra generated by the set of these operators that I call gamma. And you have 2n of them. So A goes from 0 to. And this is generated by these operators in the sense that it's all possible products and linear combinations of products of these operators. And the algebra rules are given by the fact that they satisfy these anti-commutation relations. Which just mean that they anti-commute if A and B are different and they square to identity. So in a sense, this was all that there is in terms of algebraic structure of fermionic systems. I talked a bit about how this, in a sense, actually constrains a lot what is a possible system, because we said that all the irreducible representations of this algebra are unitarily equivalent, they're the same. They have this 2 to the n-dimensional space they act on. But after having introduced this sort of abstract mathematical formalism, I tried to give at least an example of where such objects appear. And the example that I gave, say example, was antisymmetric wave functions. So here we introduce the Hilbert space as the direct sum of Hilbert spaces of wave functions of a different number of particles. So we had a sector with 0 particles and then a sector with 1 particle. And then we had like a sector with 2 particles, which is right like this. And what those who were here last time know, but what I mean by this is just a tensor product of twice the single particle Hilbert space, where I only consider this antisymmetric states in there. And then, of course, we have the same thing for three and so on. Right. And then I show that if you consider this Hilbert space, you can define certain operators. For example, I introduced this operator A, K, which acts on certain wave functions that are somewhere in there and have, for example, n particle wave functions. And this will create a n-1 particle wave function. So this is a function with n-1 terms, and I define this in a certain way. Where phi k is one of the basis elements of this single particle Hilbert space H1. So there is a certain number of them labeled by k. And what this operator does is just projects out of your wave function a particle in this state. And I also define a dagger, which kind of does the opposite. It adds a particle. So if n had n particle, now this has n+1 particles. And the wave function looks something like this. So it basically takes your wave function and multiplies now by a new particle in this state phi k, and then it anti-symmetrizes. The sum is over all permutations pi of the particles, so that you once again get an anti-symmetric wave function that is somewhere in this space. And yeah, anyway, I showed that these operators are indeed one of the adjoint of the other, and they satisfy certain relations such that if you now define your operators this way, well, these operators defined in this way for k going from 1 to n, or 0 to n minus 1, will satisfy these relations here and define our algebra of fermions. So this was an example that involved wave functions, particles, and so on. Today I wanted to talk about a different set of examples where these operators can appear, or this algebra of operators can appear, and this is examples that involve spins or cube system of spins, system of cubes. So let's say today I will talk about some, actually maybe more than one example, but it's example 2, which is kind of spins or qubits. Okay, so this was just a very quick summary of what happened last time. So if we consider now a system of spins, the Hilbert space H will be the tensor product of n smaller Hilbert spaces that represent your local elements, which in this case we want them to be qubits. So each hk is just a two-dimensional Hilbert space, and on each of these hk's we have the usual Pauli operators, which will appear later, and I label them in this way. Now the dimension of the total Hilbert space is 2 to the n. So this should, ring a bell with what we said last time, that essentially all the representations of that algebra live in a Hilbert space of this size. So it should be possible to define some operators gamma in this Hilbert space which satisfy the right commutation relations. And this is indeed possible, and it's not actually so hard to find them. It's actually pretty easy to define them, and indeed one can define them in the following way. Okay. Right, so these are just a set of operators that I have defined, and they are Pauli operators, and contain a string of Z operators going from 0 to k minus 1, and then on the kth qubit they have either x or y, depending whether we consider an even or odd of these fermionic gamma operators. And you can immediately see that these satisfy the right algebra relations. They square to 1, and if you take two different ones, they anti-commute, because if k is the same, then all the z's commute, and you just have x and y, which anti-commute. If the k is different, then again, everything will commute, except one of these strings will be shorter, so one of the x's will end up acting on the same site as a z, or vice versa, one of the y's. But in any case, x and z, or y and z, anti-commute. So these clearly satisfy the algebra that I wrote before. And one thing which we talked about the other time was that one can introduce these n operators, occupation number operators, which we defined last time in this way. And one can ask, what do these look like in this case? And one just needs to take the product of these two things, and you will see that what you get is so these are just related to the Pauli Z operator. So essentially this occupation number, which we use to define this occupation number basis, as the basis of common eigenstates of the n operators. This is essentially just the computational basis, because it's the basis where the Z operators are diagonal. Right. So, in this case, it's in this setting, it's maybe almost trivial to construct some operators which satisfy this fermionic algebra and see what they are. The main drawback is that now these operators are, let's say, not exactly the most natural operator that appears in usual spin theories, like some very high weight operator that it's not clear why it should appear at all in your normal spin or qubit theories or your usual qubit gates. And this is definitely the case, but there are some exceptions. So, for example, one exception is the transverse field Ising model. If you consider in 1D. If you consider this model, then this is given by a Hamiltonian. It's a spin model given by a Hamiltonian, which has this form. So you have some kind of nearest neighbor XX coupling, and then some field in the Z direction. And you can try to rewrite these operators in terms of these operators here, and you can see that it's not so hard to do. You can, if you want to check that this is equal to the following. The fact that this is equal to Z we saw before, and same here, like you have two different gammas, so there will be all these strings of Z which cancel each other, and you're just left with two X operators. So this is a kind of a particular example where Hamiltonian, which looks kind of simple or natural in the case of spins, also looks equally simple and natural in the case of fermions. You can have a combination of low weight operators in this gamma. In particular, this actually, once you write it this way, you see that this is an element of this set that we called Q. The other time, these were the set of quadratic Hamiltonians. With respect to these fermionic operators, which we discussed, they are particularly nice operators. So in this case, this Hamiltonian, once you rewrite it in terms of this gamma operators, is particularly nice and well behaved. But of course, you see that this fact is kind of fine-tuned in the sense that as soon as you change this here, this is drastically not the case anymore. For example, if you add an X field, this will no longer be the case. You will get here big strings of gammas. If this is not in 1D but in 2D, same. If you don't have nearest neighbor, have more than nearest neighbor coupling, it's the same. So this is kind of a only a relatively fine-tuned example where this happens.
Sorry.
Yes.
So is there maybe, Mr. But is there some intuition behind how this spin example corresponds to the idea of something being fermionic, or this whole number operator, like occupation number thing? Like we showed mathematically that it satisfies the relation, so we by our definition it's fermionic, but from a more physics point of view, is there a simple idea on why this is?
So I think the point that one has to understand here is that there is a direct isomorphism between this 2 n-dimensional Hilbert space and the one of fermions that we introduced kind of abstractly before. So in a sense, any state in this Hilbert space has a equivalent corresponding state in the fermionic Hilbert space, and this mapping between states is very easy. You just transform this, map this to the computational basis. So this is a very easy transformation to do. And at the same time, any operator, so any Hamiltonian or something, also has a equivalent writing in terms of these operators, gamma. So in a sense, any Hamiltonian, any spin Hamiltonian is fermionic in this sense. So I think what really matters is it not if it can be written as a fermionic operator, but if it can be written as a, somehow what you would naturally or physically be willing to call a Hamiltonian in the fermionic case. And here, I think a reasonable definition of that is a linear combination of low weight operators in these gammas.
Right, yeah.
So the same way that here, if you have a sum of big Pauli strings, you wouldn't call this like a natural Hamiltonian.
Right, yeah. So it's less about being fermionic, but more about being in Q in a way.
Yeah, or I mean, if you also find something that has maybe four order terms, you would call this an interacting fermionic theory or something like this. But if you have something with order n, power of n terms in these gammas, then that's just something weird.
And also, as I guess you would say, or for me, I think also important here is the 1D thing. If you just have a weird lattice where some spin interacts with another in a weird way, depends on this graph, then it's no longer true, right? So
yeah, for sure, the fact that H, when you map it to fermions, is in Q or something close to Q is for sure not at all a generic fact. Like most reasonable Hamiltonians don't have this.
Right.
So I think saying a Hamiltonian is fermionic is not a super well-defined statement. It's more about aesthetics than anything. If you say this Hamiltonian is a free fermionic Hamiltonian, that's a much more precise statement in the sense that when you map it, you get something in Q. Yeah. And when this is true, there are very few other nice spin models for which this is true.
The logic just that spins are effectively monodromes and that they satisfy commutation relations, while fermions satisfy anti-commutation relations. No.
The logic of why this is not the case in general.
Well, yeah, you try to map bosons to fermions, but that's effectively two-dimensional bosons to fermions.
Yes.
And that's what you are doing here. That's not that. It depends on what is weird, it depends on what you think will be the natural commutation relation of objects.
Yeah, you can say it this way. I think, depending on what you think you are describing, there are some objects which are natural and there are some which are not. If you are describing fermionic particles, like the ones we talked about before, the natural objects are things that anticommute. And if you now try to create objects that anticommute out of the natural spin objects, this is not doesn't come for free because they don't naturally anticommute the natural spin objects. Whereby natural spin object, I mean, are Pauli images. Right. So okay, this was the fact that now we mentioned this Q operators brings me to the next question, which is that last time we talked a lot about these Gaussian or free fermion unitaries in the context of fermions. And one might ask the question, what do these in general look like now if we write them as spin operators with this mapping? And this brings us to this idea of match gates. So we'll consider a unitary, Gaussian unitary, which I defined last time. For those who were not here, this is just exponential of some quadratic polynomial of the gammas. And one wants to write this in terms of spin operator, like a generic Gaussian unitary. We want to think about what it looks like in terms of those spin operators. And to do this, the first observation that one can make is that any Gaussian operator defined in this way can be written as a product of a certain number of other Gaussian operators, where each of these individual terms has the property that it only involves, let's say, two subsequent fermions. So maybe more precisely, let's say ui is Gaussian, so it's the exponential of some quadratic term, where this quadratic term now only involves, for example, gamma to k plus 1. So it's like the kth fermion and the k plus 1 fermion. So gamma to k plus 1 to k plus 1. So this is just a second order polynomial of these variables. So you kind of should believe me that it's possible to decompose any Gaussian unitary in this way. This follows essentially from the fact that you can do this decomposition for orthogonal matrices, and we saw last time that this is essentially a group representation of orthogonal matrices. So if you can do it for orthogonal matrices, you can also do it for these. And from the point of view of orthogonal matrix, this is related to these Gibbons rotations. The fact that you can decompose it in this way.
So that Gibbons rotation are not particular representative?
No, I mean, okay, I don't know. But
Okay, I mean, Gibbons rotation gates, I knew that they were, I mean, but probably you are talking about orthogonal.
yeah, so for me, this means that if you forget about fermions or anything, I give you an orthogonal matrix, you can always decompose it into a product of orthogonal matrices where each matrix is non-identity only in one block, 2x2 block, essentially.
Nearest neighbor.
Exactly. Yeah, but you first basically decompose it in not the nearest neighbor, but 2x2, and then you can put in some swaps to make it nearest neighbor or something like this. But yeah, this can be done. This can always be done. So once you do this, then we can focus on one of these individual terms, and for example, consider the one that involves the first four of these operators. And if you now are considering quadratic operators in these four terms, then there are not so many options. In particular, there are 6, which I will try to write down. And now you want to rewrite this in terms of the Pauli matrices, again, using the mapping that we did before. And you will see that, for example, this one is proportional to Z times identity. This on the first qubit, this on the second qubit. This one will give you something like Y, X, Y, Y. X, X. So you can sit down and do the computation. You see that these are the only operators that you get out. And if you now consider that this Q is basically any linear combination of these 6 objects, you can try to write out explicitly these matrices in the computational basis of 2 qubits, and you will find big matrix that I will try to sketch. We basically find something that looks like this. But this is really just the normal basis. Then you will find something here. So you can write these things out explicitly, and you see that linear combinations of them give you a matrix that looks like this, where you see that this matrix is block diagonal in 2 4x4 blocks, like one involving 0 0 1 1 and 1 0 1 1 0. And inside each of these blocks, you get basically the most generic traceless Hermitian matrix. So if we now want to write u in this basis, u is the exponential of I times this. So this will also have, if we now exponentiate, we get something that has the same structure. Where this u and v are 2 matrices which are exponentials of something Hermitian and traceless. So these are matrices in SU2. So in conclusion, all Gaussian unitaries, when written in as qubit operators, are the group of all possible products of nearest neighbor gates, where each individual gate must have this form, a 2-qubit gate of this form, which is some kind of specific subset of 2-qubit gates. And the set of all gates with this form was actually studied or introduced even before people realized that this was equivalent to these fermionic Gaussian operators, and they are these match gates. Match gate unitaries of circuits, I don't know. So yeah, in this language, match gates are exactly the same thing as what we call Gaussian unitaries the previous time. Yes?
Okay, sorry, so you showed that thanks to this the composition of the matrix, fermionic, any fermionic unitary can be decomposed as a product of nearest neighbor match gates.
Yes.
Vice versa, instead, like any nearest neighbor,
so a match gate circuit contains in its definition that you have 2-qubit gates like this acting on nearest neighbor qubits.
Yes.
So that's the definition of match gate.
Okay.
The nearest neighbor thing is built in the definition.
Okay.
And
this shows the equivalence between
yes.
match gate circuits and
yeah, because if you have a circuit that is built of gates like nearest neighbor gates like this, you can do the vice versa, and you can always write them something like this, which in turn means it's Gaussian. But it's important that these gates only act on subsequent qubits, otherwise, like this step doesn't work. Right, so yeah, maybe. Okay, so this was like, let's say, the easy way to find fermions in qubits, in the sense that it was easy, because the construction was quite straightforward, but it was maybe not so nice in the sense that you get these operators gamma that look a bit funny and not so natural and not so local, and they don't, maybe not so satisfying in general. So, however, there are also other ways to find the fermion algebra inside spin-based systems. Of course, there you have to pay a price that the construction is maybe a bit more convoluted, and there are caveats and things like this, but ultimately you can get gamma operators that look a bit nicer and are a bit more local. So I wanted to give another example of how this can be done. And that's the last thing that I wanted to talk about today. So,
sorry?
Yes.
Can I ask one more question about the SU2
Sure.
thing? So there's this relation, right? That SU2 times SU2 is like isomorphic or double cover of something, like in relation to SO4, basically.
Yes.
And is that basically the bridge in the Lie algebraic framework between this and the orthogonal matrix idea of the?
Yeah, I think everything should match, because if you consider now just a single gate of this type, then this, from the point of view of qubits, is, as you say, SU2 times SU2. And from the point of view of fermions, this is a Gaussian gate on 2 fermionic modes, which last time we said is equivalent to SO2n, so in this case SO4. So you would have here you have SO4, and here you have SU2 times SU2, which I think are a connection that you were making.
Yeah. Okay.
Okay, so what I wanted to give an example now, how you have also fermions can appear as local excitations in topological models. So here the nice thing is local. The not so nice thing is that one has to work a bit harder to get it out, but hopefully we'll get there. And so already I will start with a caveat, which is that in order to make this work, we will actually not try to represent the whole Clifford algebra, but only the even subspace of the Clifford algebra. I guess I call it plus. And this is basically a subspace of even products of these gamma operators. So this is the things that look like when you have a 0 term plus. No, sorry, you don't have alpha 1, alpha 2. So we will only attempt to represent objects of this type. This is a sub-algebra in the sense that if you take products of these things, they will again be even. So it is closed under products and then linear combinations. And to try to represent this, I will now consider a spin system that lives on a hexagonal lattice. So I will now attempt to draw an hexagonal lattice, also known as honeycomb lattice. Something like this. So the idea is that I consider a system like this, and I now place a spin on every vertex. And I want to consider a system such that in the end there are 2n spins, so 2n vertices, which means that kind of the Hilbert space will be 2 to the 2n. And in particular, actually, I will care about a subspace of this Hilbert space, which I might as well introduce now. I call it F. You can guess why. Which is basically states in this H such that LP for every plaquette, where so there is, the graph has many plaquettes, and for every plaquette I define an operator L, which is in the following way. Basically, I'm acting with some operators on the vertices of a given plaquette in this way. So this is like a stabilizer code subspace of H defined by these stabilizers, which all commute. And if you have 2n qubits, you see that there will be order n plaquettes in this system. So you have order n constraints. So in the end, the dimension of this F will be 2 to the n. I mean, you have to be a bit careful here with the boundary conditions. Not all the L's will be independent, but maybe it's 2 to the n plus 1 or something like this. It doesn't matter too much. Or at least I don't want to get now into the figuring out the right boundary conditions. And okay, so I would like to define now in this system, or find somewhere in there, the fermionic operators for a system of n fermions. So basically there will be one fermion for every 2 qubits. And this, you can see it in the sense that in this kind of lattice, the unit cell is made of 2 sides. So, this would be a unit cell. And you can repeat it around. So for every unit cell, I will label them by the index k. So each one of these groups has, I label it by k. And basically for any of these unit cells, I will end up defining this usual gamma. For each of these unit cells. And I will use the notation that I will label each unit cell by k, and then inside the unit cell I will have the spin A and the spin B in this way. Okay. So what I can define, or maybe first let's look at the picture one last time. You can see that in this lattice there are basically 3 different kinds of bonds. So there are the sort of horizontal ones, and then there are the 2 different types of diagonal ones. So I'm going to define a different kind of operator for each bond. And particular, for example, I will, maybe one can even use colors. I will define, I will call these bonds that are the ones that are kind of inside each unit cell, the Z direction. And I will define a bond operator on each one of these bonds that acts with the Z Pauli on each qubit. And then I want to define also the Y bond in this way. And these horizontal ones, I call them X bonds, and I act with X on each qubit. So this is kind of the picture in formulas. I would like to define a bond operator of type Z, number K, as acting with Z operators on the 2 qubits of this unit cell K. So with the notation I introduced before, something like this. And then I can also define the ones of type X. As acting on the qubit, with X on the qubit in this unit cell K, and with X also in the qubit on the next unit cell by moving in the X direction. I write it in this way. Right, so if we consider this case here, this would be kind of in the unit cell K, and then this would be the what I call the X unit vector, and this one is in the unit cell translated once in that direction, and similarly this direction will be the Y. And so I can define also this operator. Now, my claim is that these operators can be mapped naturally to fermionic operators in the following way. I do this mapping. Right. So each of these contains the product of one even and one odd gamma. In this case, the ones of the same fermion. In this case, is one from two neighboring fermions, either in the Y or in the X direction. And my claim is that if you now consider these operators and you consider the algebra generating by taking all products of them, you will find something that is exactly equivalent to this even sector of the Clifford algebra. And you can let's try to see why this is the case. And the first thing that you can check is that they satisfy the right commutation relations, in the sense that these operators, if they are truly fermionic operators, yeah, as I said, they all contain one even and one odd operator. So if they are acting on completely separate fermions, they should all commute. And if they are acting on neighboring fermions, then maybe the K is the same as K, then these two operators will anti-commute with each other. Or if maybe the even operators match, and then, anyway, they will only match on one gamma, and then they should anti-commute. And you see that it's essentially the same thing is happening here. If these two are acting on the same qubit, then they will anti-commute, or X will anti-commute with Y, or something like this. So I think you can convince yourself fairly easily that these satisfy exactly the same anti-commutation relations that those ones we expect to satisfy if they are truly fermions. There's questions, or if you don't see it, let me know. So I think one can say that commutations say check, we believe it. Then the next point is that I'm saying that if you take products of them, you can reconstruct the whole, you can generate the whole algebra. And this you can see because you know, the algebra is generated by even products of gammas. So you can always, if you have a certain product of gammas, you can consider like blocks of two gammas at a time. So one just needs to show that one can, you know, reproduce in terms of these B operators any operator that is the product of two gammas. If you can do this for any operator of this form, then also the higher powers of this will work. And so, for example, let's consider two even gammas, but one can do exactly the same thing that I'm going to do. One can do exactly the same thing also for two odd or one even, one odd. And so let's say that we want to represent somehow these two gammas acting on operator on fermion K and fermion L. And this K and L will be, you know, somewhere in this network, in this lattice. And then, you know, if one is here and one is here, one basically just needs to find a path along this graph that connects them. And then one can represent this product of two gammas as a product of B operators along the path that connects them. And one can see this relatively easy because, for example, in this case, I can rewrite this object in the following way. I can copy 2k1, and then now I introduce, for example, gamma 2k plus 1. But this square to the identity, so if I put it twice, I'm not doing anything. But I notice that, for example, this object here is exactly something of this form. So I already one of these bond operators appeared. And then I continue here. For example, now here I can introduce gamma to K2, where now K2 is the next fermion on this path that I drew that connects the two of them. So K1 and K2 are now neighbors, either in the X or in the Y direction. And again, I should put this twice, such that I'm actually just adding an identity. And then I continue adding along these gammas along the path until in the end I find I reach I can copy my KL. So here I will get something like and then now you see that if I now group them 2 by 2 in kind of the opposite way to which I introduced them, these are all corresponding to bond operators of this form, because either they are, gammas on inside the same unit cell or on neighboring unit cells. And so you can see that, this first one is just the Z terms of K1, and for example, this one will be either an X or a Y. Depending whether K2 is in the X or Y direction compared to K1, and so on until you get. So anything of this form can be written as a product, a string of B operators along a certain path. So, so far it all looks good. It seems that we can indeed generate a whole even fermionic algebra. One last caveat that one might notice here is that now we've said that these operators, I can represent them in terms of B operators by concatenating B along a certain path. But you might realize that there are different paths connecting any 2 points, right? So if I want any of this to make sense, it should be that the 2 paths which connect, 2 different paths which connect the same 2 endpoints should give the same outcome. And the fact that 2 different paths with the same endpoints are equivalent is like the same as saying that a closed path is equivalent to the identity, which is something that we should check. And now the smallest closed path is a loop around one placket. So maybe let's consider that example should be clearer what I'm saying. So for example, if we consider a single placket,
and then you get the condition that is in the subspace of this placket.
Don't spoil it. But yes. So consider now a placket, and now I act with all the B things along the placket. So this was like a BY. And what does this give if I now try to write, for example, these B's in terms of the fermionic operators that they're supposed to correspond to? In order to write this, I need to tell like what are these, like let's say that this is what I call K2, this K4. So I mean, let's suppose that we label the unit cells in this way, just to be clear. Then I can expand this B operator in terms of the gammas. And you see, like, starting from here, this will be like I gamma. It's kind of connecting K1 with K2. So this will be something like this. And then the next one will be a Z1, which is instead something like I. And maybe I can quickly write it out for all of them. So this, I just rewrote all these B operators according to their definition in terms of the gamma. So you see that have operators connecting these various unit cells K. And if you now look at this expression, you will see that every gamma appears twice, basically. Like this K2, 2K2 appears twice, this appears twice. Sometimes in order to match up the pairs, you need to do some anti-commutations, but you can check that the signs that come out from the anti-commutations cancel out exactly the signs that comes from this product of i's. And so you get that in the end, this is just exactly equal to the identity. Because all the pairs are going to match up and multiply to the identity. But now if we look at this B's in terms of the spin operators, so in terms of the Pauli operators, what does this look like? This, we can just, this ZZ is like Z, and then you have XX, Y, you apply all the bond operators in the way we've defined them before, and again here there will appear some factors I which cancel, but ultimately each one of them is proportional to acting with a Pauli on each. You can check that this is equivalent to this Pauli string acting on the lattice. And this is exactly this operator that we called LP at this time, if you remember. So here you might see that suddenly our construction is not so correct as we thought it might be, because this operator, which should be the identity, is actually something that is clearly not the identity. So here we are a bit sad, but we realize that actually we introduced the subspace F, which was defined precisely by the fact that on F, these operators LP act like the identity. So the idea is that one can try to restrict, we can restrict ourselves to only consider F. And indeed, you notice that these operators B, they all commute with the LPs, which in particular means they preserve the subspace F. So if I have a state in F, this implies that also B psi is in F for any of these B's. So if I now consider a state that is in F, and I act on it with all these fermionic operators written in terms of the B's, I will stay inside F. And if I stay inside the subspace, these loops, which should be the identity, are essentially do act like the identity. So from this, we conclude that actually the correct statement is that these B operators restricted to the subspace F generate the even Clifford algebra. And if you want to see it more like visually, you can basically imagine that these B operators, if you write them out in a big basis where you put first the basis elements corresponding to the subspace F, and then everything else. Then in this basis, these B operators are block diagonal, so this will be 0. They don't connect F with the orthogonal complement. And inside here, you have some rubbish, or something else. But this block here, acts exactly like the fermionic operators are supposed to act. So if you constrain, restrict them to F, then you get your fermionic algebra. And this kind of should make sense because we saw at the very start that this F subspace kind of has the right dimension for what you expect from n fermionic modes, unlike H, which was clearly too big. So we have to restrict ourselves. So you see, this construction is a lot more convoluted, and you have to restrict yourself and only consider the even algebra and so on and so forth. But ultimately, you get a nice mapping where something that is kind of local and nice in terms of fermions is mapped to something that is equally local and equally nice in terms of qubits.
I have another
Question.
So it seems to me that the fact that you at the end got the locality, it was because you restricted yourself to even Paris sector. If you have the other ones, I mean the other one, can you do that? There are local maps in your map?
No, I mean if you consider the odd ones, then there is no hope, because then you have things that should be local, like even the gamma. They can be local on two completely opposite sides of your system, but they still need time to compare. So this kind of violates already at the start any definition of locality or even causality that you might consider. That's why.
Also, my understanding about
That's why restricting yourself to the even subspace is something that, from the physical point of view, is extremely natural. You can expect that any physical theory will only contain even terms. But yes, if you want to represent the whole threefold algebra, if that's what you care about, then yes, you will never be able to do it locally.
Yes, there was another question from Ansgar actually about the previous example.
Okay.
So let me real quick. Can you comment on the Katav chain with which has Majorana excitations? Because the transverse field Ising model is not fermionic in the sense that its elementary excitations are not created by fermionic creation operators or Majorana operators, right? In the last part, in the Kitav chain, the Majorana operators create some excitations, and this is robust against arbitrary weak perturbations, and that's what makes it Majorana in a physical sense, right? I hope you understood the question,
Yes.
because I didn't.
Yes, I mean, I understand, and I think it's correct what Ansgar says. In this Kitaev chain, I mean, that's a model that you write directly in terms of fermions. So, where is it? Yeah, basically, it's a model that you will write in terms of something that looks like this. Actually, I've never thought about what it would look like in terms of Pauli images if you do the mapping for that one. I don't know. But yeah, for that model, you have this Majorana edge modes in the sense that you can find that in a certain phase of the system, one of the gammas at the edge, like at the two ends of, for example, a chain, will sort of decouple from the rest of the system, and you can you have an excitation there in the sense that this gamma, it can have two states that have the same energy because it's completely decoupled from the rest of the Hamiltonian. So you have this gapless edge mode and so on and so forth. But yeah, I don't know. I've never thought about how I would describe this in terms of spins and whether the excitation is fermionic in what sense. So yeah, my answer is that I don't even know what was the specific question.
Same.
Okay. Okay, so there was no question, so I didn't. Yes,
right.
It's true.
Yeah. I mean, if there's a follow-up question, I guess you'll type it and then you'll clarify.
So the reduction from 2 to the power of 2n to 2 to the power of n comes because you project into the subspace of the two spins, right? Because you have two spins in one unit cell.
Yeah.
It would be like a 4-dimensional space, but you only consider, you make one fermion out of it.
Yeah, I
So
mean,
you lose two states.
Pictorially, you can say that I create a fermion out of two spins. More mathematically speaking, I say that my valid states, like my valid fermionic states, are only states that live inside the subspace, which is a lower dimensional subspace defined in terms of the big Hilbert space. I mean, the one interesting fact is that the states inside this F are actually quite non-trivial states. They're like these topological states, like they have a long-range entanglement and Kitaev things going on. Yes, so you gain this fact of the locality of the operators by paying the price that now the states are things that look not very, or let's say, local states that you could consider local from the fermionic point of view are mapped to states that are definitely not local from the point of view of the spins.
But this fermionic mapping, does it also work if you consider different stabilizer, if LP is maybe -1 on one plaquette and +1 on all the others. So all these different plaquette coverings, basically.
I think you can, inside each of these subspaces, you can define different Bs, which will then act as fermionic inside that subspace. But yeah, you need to redefine the Bs in each.
Okay.
I guess there will be some signs, or maybe you need to change the X with the Ys or something. But yeah, the same Bs will not act fermionic in all the subsectors. Yeah, because I mean, if you act with these Bs in a sector where one of the LPs is not 1, then you have that loops are not identical, so there cannot be fermionic.
So if you try to prove this close thing for more complicated paths, no, that are not just single plaquette, what do you?
Well, you can see that any more complicated path can be written as a product of many plaquettes.
Right, in all the plaquettes inside.
Yeah, exactly. So I didn't show this, but from this you can easily show that now any path is identical.
And and the first example that you gave the other day, and today you recall.
Yes.
So this is nice, no? Where did you? How did you come up with it? Or this is
Which example?
You know. So I have this H1 can be, you know, any L2 space.
This
no?
one.
Yeah.
Yes.
So there
this
be
is-
the polynomials or whatever in 0, 1.
Yeah.
And then H0 is the canonical one-dimensional vector space,
Yeah,
no?
exactly.
Exactly. Then H1, and then I just, and this phi k are these Hermite polynomials or whatever, you know,
Yes.
some, and then I just, I can define an infinite, because this case label all this.
So if H1 is finite dimensional, then at some point these antisymmetric products will vanish, right? So at some point you need to stop. But if you have, for example, if you consider H1 to be the square integral functions on the interval, which is like an infinite dimensional space, then you have infinite number of modes,
Right.
and this can go on.
Exactly, and these are operators, in the space of the square
But it's-
variable, antisymmetric in square integral on n variables. So nice.
I mean, this is a complete standard. I mean, I think this is, if you ask someone who is more from a physics background, I would say this is the normal definition of
I think it's this is the best taken from this talk, because you really show different ways in which fermions can be constructed of this, even in this L2 spaces, because we are too used to this.
Yeah.
No?
I mean, I purposefully gave
Exactly.
this example
I think
first
that
because
was
I don't
the
want
strategy.
people to think that fermions are Pauli operators. Yeah, that's it. That's all I had to say.
So if there are no more questions. Jonas?
No, it's also not important if we heard it already. Oh, but I wanted to ask if you were to simulate a fermionic system on a quantum computer, if you would use the last mapping that you showed, or if you would use the
No, I think this one for sure. I mean, okay. If you're going to simulate a 1D chain, then it doesn't matter. But if you want to simulate a 2D model or something like this, then of course this mapping is much better, because you need to prepare a state in F to start with. And this will, in order to prepare a state in F, you need to do a linear depth circuit. This is inevitable.
Okay.
But then once you do this, sorry?
If you use measurement, then you can also.
Okay, yes.
Okay.
Linear depth unitary circuit. If you use measurements, you can probably get around like adaptive stuff. But once you prepare the state, then your whole fermionic calculation, like a fermionic operator, maybe using your Hamiltonian, whatever, maps to a local spin. If you do the Jordan and Wigner one, then each time you act with one of these, you need to do something at S depth L.
Yeah.
So of course, this is already a big improvement.
So even though you hide part of the complexity in the initial state, it's not enough to.
Yeah. So I think the point is that you're not really, the non-locality is not disappearing, but of course, what you care ultimately about is number of gates. Then this is bad.
Yeah. Okay.
Okay. With that, if you maybe do we have a final conclusive answer to the question, what is a fermion? To tie this whole thing off.
Yeah, I mean, it's this Clifford algebra, but it appears in many places.
Right.
So it's a very rich phenomenon, even though very simple from a mathematical point of view.
Okay, cool then. Thank you very much, and have a nice evening.